Hey there, welcome back to 22. And today we're going to talk about explanations of some of the things in the dot product section. So over here I have some drawings and a definition of the dot product. And then over here I have some work that I did earlier to help me understand how we were going to do this part, or at least one of the parts in here. So let's start here. So we want to derive the, here's our goal, derive the geometric form of the dot product of two vectors. Okay, and so here's what we're going to do. So we start with our two vectors, u and v, and we also form the vector u minus v. If you remember from our vector algebra section, this is what that vector looks like in geometric form. And then we're going to label also this angle theta down here. So we know up here that our vector dot product looks like that, but we want to derive the one that involves the cosine of that angle. And so what we do is we start with the law of cosines. Now this is written a little haphazardly, so I'll write it again. Law of cosines. Let me zoom out a little bit so you can see what's going on a little bit better. So we have our triangle over here formed from vectors, and the lengths of those triangle, or of the legs of that triangle, are the norms of each vector in the side. So what we can say here is, all right, well, I'm interested in the angle theta, and the law of cosines says, all right, well, if you're interested in the angle theta, you also should be interested in the length of that side over there. And so we have this sort of pseudo Pythagorean theorem. The length of the opposite side squared equals the length of the other two sides squared and added together. So that's these two sides. And this looks like the Pythagorean theorem, but the law of cosine says, not quite. You have to have this little error correction term where you subtract off twice the length of u times the length of v times the cosine of the angle between them. All right, the cosine of the angle on the opposite side to the side we're interested in. Okay, so now we have this equation, and what do we do? Well, let's rearrange some stuff. So what I want to do here is bring this term over to the other side and this term over to the right side. Swap those two. And what do we get? 2 norm u norm v cosine of theta. And you can probably already see that this is what we're going to get at the end. That's what we want. And over here we have u squared. And then let's put this in the middle, minus norm u minus v squared plus norm v squared. Okay, and now let's go ahead and focus on this term for a second. So let's bring that outside of the equation, and we'll work with that and see what we end up with. So if you remember, there is a property of the dot product and the norm that says, all right, given any vector w, its dot product with itself is equal to the norm of that vector squared. And that's what we're going to use over here. So let's see, that means we have u minus v dot u minus v. Just following this formula over here. I have norm of a vector squared equals the dot product of that vector with itself. Okay, well, now we remember that the dot product is distributive, and that means that I can FOIL this out. Normally, I might have to be a little careful with commutativity, but we also might remember that the dot product, other page, the dot product right here is commutative. So we have this property, and the distributivity property right here. So commutativity, that guy and that guy are the ones that we're using. And let's see if we go back over here, what this ends up being. So we have u dot u, and then minus u dot v minus v dot u plus v dot v. All right, and now we can use this property again, but in reverse this time. So now we take a dot product and turn it into a norm. Do that for both u and v. So right here we've got norm of u squared, and then by that commutativity, these two things are the same, so I can combine them as like terms. 2u dot v, and then plus norm of v squared. All right, and then so that's what's going to go right back up in there. We'll write it down below that. So we have our equation that now looks like 2 norm u, norm v, cosine of the angle equals u squared. And now we're substituting in our yellow expression, but we have a minus out front on the whole thing, which means that we have to put a minus here, double minus there, which makes it a plus, and then a minus there. So we swap the signs of everything in there. So let's do that. We have minus u squared, ooh, that looks good, plus 2 u dot v minus v squared plus v squared. And that is very good for us because that means that the normed terms cancel out. All right, continuing, we have so we have this term on the left side, and then this term is the only one left over on the right side. Notice that both have a 2 in them, and so we can also cancel the 2's. Do that in blue to note that we're doing that separately. And finally, we can write down our expression that norm of u times norm of v times the cosine of the angle is equal to the dot product of the two. And that is our formula there. Okay, so that's our derivation of the geometric formula for the dot product, coming straight from some trigonometry and the law of cosines. All right, so now what? Let's go ahead and derive the algebraic form of the dot product from the geometric form here. So now we're going to pretend that we don't know this formula, and we're going to show that it works. I'm going to simplify our work ever so slightly, though, and only do it in 2 dimensions. So I will omit the third coordinate. You can do the same thing in 3 dimensions. It is just a lot more difficult because you have to use spherical trigonometry. There is an easier way, which I'll show you right after, but I want to show you how to do it the trigonometric way so that you have some practice with this. Okay, so what do we do? Well, we start by writing down what we know. We know that u dot v equals this formula, and that's for any 2 vectors, u and v, cosine of the angle between them. And then over here in this picture, we note that, okay, well, we have a coordinate system, x and y, and in vectors, those coordinates are specified by the I vector and the j vector, and you say these guys have unit length. So if these guys are our units, they're sort of like the inches on our ruler, then we need to look at, all right, what is the component of u in that direction? Well, the component of u in that direction is the scalar projection, or we can look at just the projection if we want. So what do we need? We need u1 and u2 and v1 and v2. So u1, let's just do one of these. Let's see. So I've labeled some angles in here. Let's keep going here. So u1 is going to be the component of u in the direction of I hat. There we go. And if you remember the formula for that, that is I hat dot with u divide by norm of I hat. All right. And, well, norm of I hat, we said that was 1. We set that as our unit, so we don't need to worry about that. And that means that our u1 component is just u dotted with I hat. Okay, but now our dot product formula here says, well, I know what that is. That is norm of u, norm of I, times the cosine of the angle between them, which I've now called alpha over here. So we have this alpha, and then theta, and then beta over there. And this is what we want to try and end up with. Except we also know that that's 1, so we can cancel that out as well. So what do we have? We have that u1 equals the norm of u, its length, times the cosine of the angle between u and the x-axis, the positive x-axis, I should say. Okay, so this is sort of the thing that we're looking for. Now, what do? We can start with this formula, and we want to get sort of similar things to this appearing in here by rearranging or playing with the algebra and trigonometry. So if I come over here and look at this picture, what I might notice is that theta, alpha, and beta all together added up make the angle between I and j, which is pi over 2. So let's note that we have alpha plus beta plus theta equals pi over 2. Okay, well, that means that I can solve this for theta, and I get theta equals pi over 2 minus, and I'll just put alpha plus beta here. Make our lives a little bit easier in a second. All right, so if that's theta, and I have this formula, and I'm looking for this formula, what do? Well, let's plug some stuff in, and then we'll use some trigonometric identities. So we have norm u, norm v, and then the cosine of theta, but theta is pi over 2 minus alpha plus beta here. And if you remember your trig identities, you'll remember that this is norm u, norm v, just copying these down, and then sine of alpha plus beta. That's our complementary angle formula. So we have that the cosine of pi over 2 minus t is equal to the sine of t, and the same for the sine. If you don't remember this, try and convince yourself that it's true by looking at the unit circle. Okay. And so now we have this, and we have another formula that we can use, the sum of angles formula for the sine function. So we'll write down our u, our v, and then the sum of angles formula. It's a bit long, but not too bad. It's got sort of this nice pattern of symmetry going on. Sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Okay, so we've got this thing sitting out here, and now we're basically almost there. We just have to rewrite things a little bit. So what I'm going to want to do here is put, so I want to put u and v with the correct trig functions. So what's going to happen is we'll take these guys, distribute them to each of these terms, and then we will group u with either a sine or a cosine, and v with the other cosine or sine. Let's see. Let's actually take this term and put that over here. I should have written that one first, but c'est la vie. So we've got u, v, and then cosine of alpha, sine of beta, plus u, v, sine of alpha, cosine of beta. All right. And now what do I want to do? Well, I just want to try and find this formula. And that's pretty easy to find in that first term. That's why I put the cosine alpha part there. So we've got norm of u, cosine of alpha, and norm of v gets paired with the only part left, sine of beta, plus, okay, and then now, well, u wants to get paired with the alpha stuff, so u sine of alpha, and then v cosine of beta. Notice that u went with the alpha stuff and v went with the beta stuff. Okay, so if we want, we can rearrange these a little bit, but we don't need to because we can just look at the picture up here and see, all right, well, norm u cosine of alpha, that's this leg of the triangle, and that's the x component of the u vector. And similarly, v sine of beta, so the sine of this angle beta is the opposite side. That is the x component of the v vector. So what we have is u1, let's write this a little bit more in line. So u1 times v1. And then similarly, u sine of alpha is going to be this leg of the triangle. And then v cosine of beta is going to be this leg of the triangle. So the vertical ones in both cases, which means that we have our y component of u and our y component of v. And there we go. That is our algebraic form of the dot product. Now, like I said, you can do this for three-dimensional vectors or four-dimensional or five-dimensional or whatever. The trigonometry just becomes incredibly difficult. So in 3 dimensions, you already have to deal with spherical trigonometry. In 4 dimensions, don't even ask me, but it is possible. I said that there was an easier way to do this, and there is. What you have to do is note that, all right, well, I remember that u can be decomposed into its x component in the I direction and y component in the j direction and z component in the k direction. Same for v. v1 I hat plus v2 j hat plus v3 k hat. And we're just sweeping all of the trig stuff under the rug with this approach. And what do? Well, now we do our u dot v, and we then multiply these two things together, just like, remember these were like polynomials. I said something like I is like x, j is like y, and k is like z. And I just have to remember that x squared equals y squared equals z squared equals 1, and xy equals z, yz equals x, and zx equals y, that sort of thing. Oh, I'm sorry, that I'm thinking of the cross product, which we'll do in the next section. So no, xy equals y, z equals z, x equals 0. Okay, so that's what we need to remember here. Basically, this just turns into, all right, well, I only need to worry about this combination, that combination, and that combination, because when I FOIL everything out, I with j is this type of thing, and so it ends up being 0. J with k or j with I is this type of thing or this type of thing, and that's 0, and so on. So we really only need u1, that in, u1 I hat dot v1 I hat plus u2 I hat v2, or sorry, not I hat, j hat, v2 j hat plus u3 k hat dot v3 k hat. And what do you know? That looks like an x squared y squared z squared thing to me. And so these guys cancel out, give us just a 1 in each of these. And then we multiply the components and get u1 v1 plus u2 v2 plus u3 v3. And so that's how we get that this is the form of the dot product that we're interested in. Okay, so the last thing that I wanted to do here was show you how to interpret the dot product as the area of some shape in the plane. And it's easier to do this again in 2 dimensions, but the same thing works in 3 dimensions. So let's start with a drawing of our vectors. So I'll do a simpler one here. We've got u, and we'll put v right there. And yes, that's what I want. We've got u right here, and here's v. And what we want to do is understand, all right, why does that cosine term appear in the geometric formula? That is going to be the key to understanding how to interpret this as an area. All right, well, the cosine thing, cosine of this angle theta, if I draw this right-angled triangle with v and u, is exactly the length of this side. Quite want that to do that, but that's fine. Okay, so that is the cosine of the angle theta, and then it needs to be scaled by the length of that vector v. Right, a little small, sorry. Okay, cool. Now, well, if I interpret that thing, I know that shows up in my geometric formula as the length of a side of a shape. Well, the other length of the side of a shape that shows up in my formula, let's zoom back up here real quick. So we're looking at this formula. I already see norm v cosine theta as a side, quote unquote, in my shape. This one has to be the other side. So the norm of u has to be the length of the perpendicular side of my shape. And I say perpendicular because why not use a rectangle? Rectangles are much easier to deal with. So let's do that in blue right here. So I'm going to put this perpendicularly, and we are going to think, okay, well, I've taken u and rotated it 90 degrees to what it originally was. Okay. And now I copy u, put it over here, and where I wanted it to go. And then I'll copy v as well and paste that up here, and I'll see my shape very clearly, hopefully. So there's my shape v, and then, or my shape, and here's my vector. We'll call it u tilde because I rotated it. This is just the vector v again. This is also u tilde. And we can maybe see that if I draw another right angle right there, well, my area is the area of this rectangle right there, which is also the area of this parallelogram right here. Just take this triangle off and then put it back down over here. So they're the same. And now we have the interpretation of the dot product as the area of a specific shape in space, given that we know what our vectors look like. So let's say u dot v equals area, let's call this shape P, area of our parallelogram P. And the area of a parallelogram is just the length of one of the sides times the height of the perpendicular line. You could also think of this as one of the sides and then this as the height of the perpendicular line. And that would correspond to pairing the cosine with u instead of v. But we're going to continue this way. So we've got area of P is norm of u tilde times norm of v cosine theta. And that's just, again, length times width. And wait, I got u tilde just by rotating u. So I have that this is exactly the norm of u times the norm of v times the cosine of theta. Okay. And so that's exactly how we can interpret the dot product as an area in space, which I think makes it a little bit easier to understand and conceptualize. All right, so that's our explanations videos for section 1.3, and we'll come back in the next video with an overview of section 1.4.